Today we're going to talk about thermodynamics, and this is probably up there with crystallography in terms of the most abstract concepts that we'll talk about in the class this semester. But they're important in the sense that a lot of how we understand what minerals will form in magma or in a metamorphic rock are controlled by the thermodynamics of the crystallization of that mineral. Remember, crystallization is really just a chemical reaction. You're taking and changing the pressure or temperature or water content of a system, and it's causing something to happen. And that something happens, in many cases, the formation of some sort of mineral. So why do we have reactions to begin with? Well, that starts with Le Chatelier's principle. And what Le Chatelier's principle says, more or less, is that if you're going to change a system that's in equilibrium, the position of equilibrium will shift in a direction that reduces that change. So what does that break down to? Well, if we're going to model a geologic system, like a magma chamber crystallizing, we assume that the system starts at equilibrium. What does that mean? Well, that means that everything is in equilibrium with everything else. And then we have a change that happens. So that change might be it starts to cool. It might be a change in the concentration of stuff. It might be a change in volume or pressure, or you add a catalyst. So there's lots of ways that you can change systems. And that system will then respond by shifting one direction or another towards the reactant or the product to restore that equilibrium. So that's the basis of our understanding of predicting what minerals are likely to form during crystallization. And that crystallization in a magma body happens because we have some change in the system that's happening, and it's reacting to restore equilibrium. Because when we look at reactions, we can have three kinds of reaction types, right? The lowest energy one is something that's stable. So that's like ball C in this diagram. Ball B is unstable. That ball is not likely to sit there. So it is unstable. It is capable of a spontaneous reaction, spontaneous change. And then we have metastable, which is something that if you add some more energy to the system, that a reaction can happen. So that adding of energy is what we call the activation energy. So if you can get A to B, then you can have a spontaneous reaction from then. So we have these three different states. C is in equilibrium, B is in disequilibrium, and A is in what we call metastable equilibrium. So we have these different states that a reaction can be. And that hill in front of A to get it to B is what we call kinetic barrier. It's the energy, there's some amount of energy that's involved that you must overcome to maybe break down the bonds of that mineral so that the reactions don't happen instantaneously. So an example of this might be olivine. Olivine crystallizes at higher pressures and temperatures than the surface of the Earth. If olivine was unstable at the surface of the Earth, it would break down almost instantly. But because it's metastable, because it requires an activation energy to break down, it doesn't spontaneously re-equilibrate into something else. It will break down over time. Usually that activation energy might be brought upon by alteration from water. But olivine at the surface initially is metastable, so it will stick around. So we have these different places. We have metastable that require an activation energy, an addition of energy or catalyst or something like that. B is unstable. It's in disequilibrium. It can spontaneously change, and C is in equilibrium. It's at lowest energy. It's likely just going to stay there unless something dramatic happens. So now we can talk a little bit about the laws of thermodynamics because they end up being important as well, right? So the first one is the conservation of energy, right? So this diagram here shows a couple pistons. Work happens. but the amount of energy is conserved. So we see this increase in the internal energy of a system, and it's equal to the amount of energy that's added by heating the system minus the amount lost from the work being done. So the short of here is that energy is conserved. The second one is the law of entropy. This one's one that tends to be confused a lot. It doesn't mean that we're all going to end up in the long term breaking up into our constituent atoms, that the universe head towards entropy. It just says that over time, the entropy of an isolated system, like we have on the left-hand side of that figure, that's not in equilibrium, will tend to increase over time. And at equilibrium, it will have its maximum value. So we have this spontaneous change from highly ordered to disordered. And again, that's just our second rule of thermodynamics. And the final one is that at absolute zero, there's perfect order. So that once you have a system that is at absolute zero, all processes cease and the entropy reaches a minimum value. So as opposed to 2, where we're saying that near equilibrium, you might have a maximum entropy. For the third rule, at absolute zero, we just say everything's perfectly ordered. So those are the laws of thermodynamics. Now, why is that going to end up being important? Well, we can think about the sorts of reactions that we can have. And this has to do with Gibbs free energy. It's a thermodynamic quantity that we can use to determine if a reaction is spontaneous or not. So we want to have situations where this Gibbs free energy is, if a reaction is going to happen in a setting, let's say, of crystallizing, if a mineral is going to crystallize out of magma, it has to be a reaction where it's spontaneous. So that means that here, the Gibbs free energy of the products, the thing that's being formed, is lower than the reactants. There might be a kinetic barrier that has to be crossed to get there. But if the reactants, the magma, let's say, have a higher Gibbs free energy than the products, let's say olivine crystallizing, then that reaction will be spontaneous. On the other hand, if the Gibbs free energy is the other way around, where the reactants is lower, the Gibbs free energy of the reactant is lower than the products, then you don't have a spontaneous reaction. And instead you have a reaction where you need to add energy or add a catalyst or do something to get that reaction to happen. It's not going to happen on its own. And these reactions, the Gibbs free energy, is based on looking at things like the enthalpy and the entropy of the materials involved. And that you need to think about a bunch of these different thermodynamic parameters like internal energy and heat and entropy. These are all pieces that go into it. But for our purposes, what's important is that we can predict what minerals are stable based on looking at the chemical reaction that's required to form the mineral and looking at it at specific conditions to see if what is stable, the reactants or the products. If the products have a lower Gibbs free energy, it means those minerals will form. So we can think about putting together the phase diagram. So we have this idea of the boundary between phases. So this is a picture of a clapperon in the corner there looking at a newspaper, I guess. No, probably a scientific paper. But in this diagram here, we have temperature on the x-axis, pressure on the y-axis. And then we have two phases. We have mineral 1 and mineral 2. So mineral 1 is stable in the upper left. Mineral 2 is stable in the bottom right. But for this example, we can assume that there's a reaction that you go from mineral 1 to mineral 2. Now, at higher pressures and lower temperatures, so the upper left-hand side of this diagram, the Gibbs free energy of mineral 1 is lower than mineral 2. So it is the stable mineral. At higher temperatures and lower pressures, in the bottom right-hand side, it's the other way around. The Gibbs free energy of 2 is greater than 1. So it is the stable mineral. And then that curve that you see there is the boundary between the two, where the Gibbs free energy is the same. So what happens there? Well, it turns out that both minerals are stable along that boundary. So you would find both 1 and 2. So if you had a rock that formed up in the upper left, you'd only find mineral 1. If you had a rock that formed in the lower right, you'd only find mineral 2. But if you had a rock that formed along that combination of pressure and temperature, you'd find both minerals. And the line there is the slope of that line at any given point is defined by what we call the Clapeyron equation. Now, it doesn't tell you where the line is. It just tells you the slope. And because you can calculate this based on the chemical reactions, you can use this to design a phase diagram. And you'll do this in lab. And I'll show you an example in a second of the Clapeyron equation. But using the Clapeyron equation, you get the slope of this line when everything is in equilibrium. And once you have that, you can do experiments or calculate some models to tell you what minerals are stable in what conditions, and then plot that line that separates the two to show the equilibrium. So when we do that, we create what we call a phase diagram. So this is how the Clapeyron equation works in geology. Here we have a reaction where jadeite, which is a pyroxene, and quartz react to form albite. Here we have temperature on one axis and pressure on the other, and there's a line that separates them. So at the higher temperatures, lower pressures, you get, or at higher temperatures, you get albite. At lower temperatures on the whole and lower pressures, or higher pressures, you get jadeite and quartz. There's a reaction. Jadeite plus quartz equals albite. Along that line is delta P over delta T. That is equals the change in entropy over the change in volume. So entropy, it's hard to measure. It's not exactly a sort of thing that is easy to measure in materials. So you have to get a little clever. You have to think about how we can measure something like that. And it turns out that you can measure that by, instead of measuring it as entropy, you can measure it as the heat, the change in heat over the temperature. Okay, so before we get too lost in those weeds, we're not going to really get into that at this point. What you should take away from this is that the slope of that line is the Clapeyron equation, and that you can use that. You run a bunch of experiments that tell you where jadeite and quartz is stable and where albite is stable. And then you can devise a line that separates those two fields and then check it against the Clapeyron equation to see if that makes sense. So for these phase diagrams, we have, again, for these phase diagrams, this one is what we call a polybaric phase diagram. We have temperature on one axis, pressure on the other. We're varying pressure with temperature. So here we have water. So we have water vapor, water, and ice. The boundaries are places where both can exist simultaneously. So at 1 atmosphere and 100 degrees C, you have water and water vapor existing at the same time. The triple point down at the bottom, or down and sort of in the bottom, is a place where you can actually get ice, water vapor, and water to exist all at the same time. You need to have low pressures to do it. Space, for example. One important thing to think of here is that when you are taking ice and heating it up to form water, a couple things happen. Your chunk of ice might start at a temperature below 0 degrees C. You add energy in the form of heat, and you heat that ice up. And as the ice is heating, it's not melting. It's just getting warmer. All the energy is going into warming the ice. Then you hit that boundary right here, let's say 1 atmosphere and 0 degrees C. At that boundary, the energy is suddenly not being used to heat up the ice anymore, but rather to convert the ice to water. So once you hit that melting point, in this case we call it the solidus, once you hit that solidus, the ice will stay the same temperature until it's entirely melted, because all of the energy is going into what we call that phase transition. And once that ice and water, or once that ice is completely converted to water, then the energy can go into converting heating up the water until maybe you get to 100 degrees C, where that water, again, once it gets to 100 degrees C, that water will stay the same temperature as it's converted into steam until all the water is used up. And then the steam will begin to heat. Because the energy that's being used, being put into the system to heat things up, and to cause these changes to happen, all of the energy is being used to convert water to water vapor at that point, not heating it up again. You have to either have all ice, all water, or all water vapor to heat the system. When you're at the boundaries, you are looking at situations where that ice doesn't heat up, but rather all that energy is going into converting ice to water. Now, for most geoscience, for most geologic, petrologic situations, we don't tend to think about a wide range of pressures, mostly because it's really hard to experiment. So what we have developed are what we call an isobaric phase diagram, where we assume that the pressure is held constant. Usually it's 1 atmosphere, because that's what people were doing experiments at, 1 atmosphere of pressure. So we look at composition on the x-axis and temperature on the y-axis. So there's a lot of things going on in this diagram. Up at the very top where you see the x, where you start at that composition at x, that is entirely liquid magma. Now, as that magma cools, it will cross that first curve that we call the liquidus. The liquidus is the temperature at which the magma starts to crystallize. For water, the liquidus and the solidus are the same, because there's only what we call one component. It's just water. In this situation, we have 2 different minerals forming, A and B. So when that magma cools and crystallizes, when it hits that liquidus, it starts to crystallize mineral A, but there's still some liquid. So there's a temperature range from T1 to TE where you have a situation where you are crystallizing A from the liquid, but not until you get to point E, which is called the eutectic, do you get the rock to be entirely solidified. That's what we call the solidus, the temperature where the rock, the magma, is entirely solid, so it's become a rock. We'll talk about this in lab some, but this phase diagram shows you that if you, let's say, started on the other side of the diagram, you would crystallize out mineral B and the liquid and follow that slope down to the eutectic at point E. And it's only at point E do you crystallize both A and B at the same time. And depending on the style of crystallization, you get some mixture of A and B, but you're not going to, the final stuff that's crystallizing has that, no matter where you start, has that final eutectic composition, because that is what has the lowest Gibbs free energy for this system. All right, this gives us what we refer to as the Gibbs phase rule. The Gibbs phase rule is a way of talking about what we refer to as the degrees of freedom. How many variables can you change independent of one another? So this means, in this case, for a diagram like you see here, you can change temperature and composition. Now, in some places, you can change both simultaneously. Temperature can change, pressure can change, and they can change independent of each other. That's where you have the most degrees of freedom. So the Gibbs phase rule is degrees of freedom equals C plus 2 minus P. This is the Gibbs phase rule for a diagram that isn't isobaric. So let's say we are thinking about one that's isobaric. So this phase diagram like you have in front of you here, that gives us a simpler version of the Gibbs phase rule. It's F equals C plus 1 minus P. C is the number of chemical components. A chemical component is the pieces of the system you're looking at that are have unique compositions. So in this diagram here, there are two chemical components, A and B. You might be tempted to think that the liquid is a chemical component, but the liquid is actually just a mixture of A and B. So the two distinct chemical components are A and B. The phase is just a homogeneous part of the system. Usually we're just thinking of it, is it the solid, liquid, or gas? So when you start at point X up in the top left, you have two components and you have one phase. You have liquid. So you have 2 plus 1 minus 1. So you have 2 degrees of freedom. So that means that in that space there, the composition and the temperature can change in any direction, and they don't have to change as the other one changes. Now, if you cool straight down and you get to point 1, you've hit the liquidus, and at the liquidus, something happens. Instead of having one phase, you now have two. You have solid A plus liquid. So at point 1, your degrees of freedom become C is 2 plus 1 minus 2. So your degrees of freedom become 1, which means that if you change the temperature, the composition has to change with it. So now you are sliding down that curve towards point 2. And as you move down that curve, as the temperature drops, the composition has to change with it, until you finally get to point E, which is the eutectic. Now here you have still two components, A and B. But at that point, you have 3 phases. You have solid A, solid B, and liquid, right down in that little divot at E. So that means your degrees of freedom are 0. You can't move. You can only move once you use up one of your phases. So in this case, the only way you drop below the eutectic temperature is that you crystallize all the liquid. So you now have one less phase. You have solid A and B. Now you only have 2 phases. So you have 2 components plus 1 minus 2. You have 1 degree of freedom, which more or less means that you just cool monotonously down from point E. All right, we're going to talk about this a lot in lab. So don't feel like if it's a little overwhelming, we're going to get into it again. But it's important because this gives us a roadmap of what we expect to happen in magma. So let's say for this diagram here, if A is olivine, that as the magma crystallizes, it starts to crystallize olivine at a specific temperature, but as the olivine crystallizes, the composition of the liquid changes as that liquid magma cools. So you're going to experiment with this in lab. We're going to see how it works, but this should hopefully at least give you an idea of how we begin to model magma thermodynamically to understand what minerals we expect to find.